Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here begins the essay, the 1935 paper Can Quantum Mechanical Description of Physical Reality Be Considered Complete, authored by Albert Einstein, Boris Podolsky, and Nathan Rosen, presented a significant challenge to the Copenhagen interpretation of quantum mechanics. This essay embarks on a detailed analysis of this influential work, evaluating its core claims, dissecting its arguments, and assessing its lasting impact on the foundations of physics. The papers focus on the concept of physical reality, and its scrutiny of quantum mechanics completeness sparked considerable debate and continues to be relevant in contemporary discussions regarding quantum foundations. Our examination will proceed systematically, scrutinizing each section of the paper to elucidate its reasoning and assess its validity. Section 1. Introduction of the completeness criterion. The introduction establishes the author's definition of physical reality, a cornerstone upon which their subsequent arguments rest. Einstein, Podolsky, and Rosen propose that if, without in any way disturbing a system, we can predict with certainty that is, with probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. This criterion, rooted in classical determinism, immediately sets the stage for a potential conflict with the probabilistic nature of quantum mechanics. The authors assert the reasonableness of their criterion, emphasizing its adherence to the intuitive notion that predictions about reality should correspond to pre-existing elements of reality. They explicitly state their intention to demonstrate that quantum mechanics, as it stood in 1935, fails to meet this completeness criterion, thereby implying the existence of additional, yet to be discovered, variables for a more comprehensive theory. The introduction concludes by previewing the subsequent thought experiment designed to illustrate this perceived incompleteness. The clarity of their reality criterion is crucial, as the entire argument hinges on its acceptability. One must consider whether this criterion, while seemingly intuitive, accurately captures the complexities of the quantum world. Its strict adherence to predictable certainty may be overly stringent, while applied to a theory fundamentally based on probabilities. Section 2. Description of the correlated system. This section details the specific quantum system used in the thought experiment. Two particles, labeled 1 and 2, interacting briefly and then separating. The authors describe the system state using a wave function, psi, represented as an integral involving position variables, q1 and q2, and a parameter, p. This wave function, psi of q1, q2, is explicitly defined such that the difference in position of the two particles is precisely defined, which is given by the expression the integral from negative infinity to positive infinity of the sine of 2 pi divided by a constant h times p times the difference of q1 minus q2 plus q naught. The integral is performed with respect to p. The result is then represented as dp. The constant h represents Planck's constant and q naught represents a constant distance. They emphasize that knowing the position of particle 1 allows for the precise prediction of the position of particle 2, and similarly, knowing the momentum of particle 1 allows the precise calculation of the momentum of particle 2. Crucially, these predictions can be made without physically disturbing particle 2, adhering to their previously established criterion for physical reality. This section establishes the entanglement of the two particles, a phenomenon where their properties are correlated regardless of the distance separating them. Their specific construction ensures a precisely anticorrelated state, meaning measurements on one particle instantaneously reveal information about the other. The mathematical rigor in defining the wave function is paramount, as it forms the basis for their subsequent claims regarding the simultaneous determination of position and momentum. The thought experiment relies on the assumption that the interaction between the particles is well-defined and controllable, which permits calculations of the wave function with precision. Section 3. Argument for simultaneous reality of position and momentum. Here, the authors present the core of their argument. They reason that since measuring the position of particle 1 allows for the certain prediction of the position of particle 2 without disturbing particle 2, the position of particle 2 must correspond to an element of physical reality. Similarly, measuring the momentum of particle 1 allows for the certain prediction of the momentum of particle 2 again, without disturbing particle 2, implying the momentum of particle 2 also corresponds to an element of physical reality. They then assert that, since we can choose to measure either position or momentum of particle 1, and thereby predict either position or momentum of particle 2, both position and momentum must simultaneously possess definite values for particle 2. This conclusion directly clashes with the Heisenberg uncertainty principle, which posits that position and momentum cannot be simultaneously known with arbitrary precision for a single particle. Einstein, Podolsky, and Rosen argue that quantum mechanics, by failing to account for the simultaneous reality of both position and momentum, provides an incomplete description of physical reality. The logic hinges on the assumption that the measurement choice on particle 1 cannot instantaneously influence the physical state of particle 2. This assumption, termed locality, is a central tenet of classical physics and a key point of contention in the quantum realm. The authors believe that any reasonable theory should respect this principle, preventing faster-than-light influences. The leap they make from predictability based on measurement to simultaneous reality is where much of the ensuing debate originates. Critics challenge whether predictability necessarily implies pre-existing definite values, particularly within the probabilistic framework of quantum mechanics. Section 4. Demonstration of quantum mechanics incompleteness. This section solidifies the conclusion of incompleteness. The authors reiterate that quantum mechanics allows for the calculation of the wave function of the composite system. However, based on the measurement on particle 1, quantum mechanics assigns different wave functions to particle 2 depending on whether the position or momentum of particle 1 was measured. This assigning of different wave functions to the supposedly undisturbed particle 2, dependent on the measurement performed on particle 1, poses a problem. Einstein, Podolsky, and Rosen argue that if the quantum mechanical description were complete, each element of physical reality would have a unique counterpart in the theory, since they believe they have demonstrated that both position and momentum are simultaneously elements of physical reality for particle 2, and yet quantum mechanics assigns different wave functions depending on the measurement performed on particle 1, then quantum mechanics cannot be a complete theory. The authors emphasize that their argument does not question the empirical success of quantum mechanics, but rather its completeness as a description of reality. They suggest that quantum mechanics might be a statistically accurate but incomplete account, analogous to a statistical description of a gas that doesn't describe the individual motions of the gas molecules. The section concludes by suggesting the need for a more complete theory, one that incorporates hidden variables or a deeper understanding of the underlying physical processes. The significance of this section lies in its explicit statement of the paper's central thesis: quantum mechanics, despite its predictive power, fails to provide a complete description of physical reality as defined by the authors. The argument's persuasiveness depends entirely on the acceptance of their definition of reality and the locality assumption. Section 5. The Copenhagen Interpretations, Response and Bohn's Critique. Niels Bohr swiftly responded to the Einstein, Podolsky, and Rosen paper, challenging their definition of physical reality and the implicit assumption of locality. Bohr argued that the very act of measurement on particle 1 fundamentally alters the conditions under which particle 2 is observed, even if no physical disturbance occurs. Therefore, he claimed, it is inappropriate to speak of the properties of particle 2 as having definite values independent of the measurement context. Bohr emphasized the interconnectedness of the observer and the observed system, a central tenet of the Copenhagen interpretation. He argued that the concept of physical reality as defined by Einstein, Podolsky, and Rosen is inherently ambiguous when applied to quantum phenomena. Bohr's response effectively redefined the meaning of measurement in quantum mechanics. He asserted that measurement is not merely a passive observation of pre-existing properties, but an active intervention that shapes the observed reality. This view directly contrasts with the classical notion of measurement as a process that reveals pre-existing values. Bohr focused his critique on the ambiguity of the phrase without in any way disturbing the system. He argued that the experimental arrangement itself, including the choice of what to measure, constitutes a disturbance in the quantum mechanical sense. This disturbance, although not a physical force, influences the possible outcomes and therefore the meaning of the measured quantities. Section 6. The rise of hidden variable theories and Bohmian mechanics. The Einstein, Podolsky, and Rosen paper stimulated the development of hidden variable theories, which sought to restore determinism to quantum mechanics by postulating the existence of variables not accounted for in the standard formalism. David Bohm proposed one of the most well-known hidden variable theories, now known as Bohmian mechanics. Bohmian mechanics posits that particles always have definite positions, and their motion is guided by a quantum potential that depends on the wave function of the system. This theory reproduces all the predictions of standard quantum mechanics, but it does so by introducing non-local correlations between particles, thereby violating the locality assumption that Einstein, Podolsky, and Rosen considered essential. While Bohmian mechanics successfully reproduces quantum phenomena, it does so at the cost of introducing a complex and somewhat artificial guiding potential. The non-locality inherent in the theory also raises questions about its compatibility with relativity. However, the existence of Bohmian mechanics demonstrated that it is indeed possible to construct alternative interpretations of quantum mechanics that are consistent with experimental observations, yet fundamentally different in their ontological commitments. The existence of Bohmian mechanics provides a concrete example of how the Einstein, Podolsky, and Rosen challenge led to explorations of alternative formulations of quantum theory. It highlights the ongoing debate regarding the interpretation of quantum mechanics and the search for a deeper understanding of the nature of reality. Section 7. Bell's theorem and experimental tests of local realism. John Stuart Bell formulated a theorem in 1964 that provided a crucial link between the philosophical debate initiated by Einstein, Podolsky, and Rosen and experimental tests. Bell's theorem demonstrated that any local hidden variable theory must satisfy certain inequalities, now known as Bell inequalities. Quantum mechanics, on the other hand, predicts violations of these inequalities for certain entangled states. This meant that it was possible to experimentally test whether nature behaves according to local realism or according to quantum mechanics. Numerous experiments have been conducted to test Bell's inequalities, and the overwhelming consensus is that they are violated, confirming the predictions of quantum mechanics and challenging the assumptions of local realism. These experiments, such as those conducted by Elaine Aspect and others, provided strong evidence against local hidden variable theories, suggesting that either locality or realism or both must be abandoned. The experimental violations of Bell's inequalities have profound implications for our understanding of the fundamental nature of reality. They suggest that the universe is fundamentally non-local, meaning that events can be instantaneously correlated across vast distances in a way that cannot be explained by local interactions. The experiments related to Bell's theorem provided empirical evidence that directly contradicted the core assumptions underlying the Einstein, Podolsky, and Rosen argument. Section 8. Quantum entanglement and quantum information theory. The Einstein, Podolsky, and Rosen paper despite its initial aim of demonstrating the incompleteness of quantum mechanics, ironically paved the way for a deeper understanding of quantum entanglement, a phenomenon that has become a cornerstone of quantum information theory. Quantum entanglement, the very correlation that Einstein famously dubbed spooky action at a distance, is now recognized as a powerful resource for quantum computation, quantum cryptography, and quantum teleportation. These technologies exploit the non-classical correlations between entangled particles to perform tasks that are impossible with classical resources. Quantum entanglement is not merely a curiosity of the quantum world, it is a fundamental resource that can be harnessed to revolutionize information processing and communication. The strange correlations between entangled particles, initially seen as a problem for quantum mechanics, are now understood to be a powerful tool for manipulating and transmitting quantum information. The exploration of quantum entanglement, fueled in part by the questions raised in the Einstein, Podolsky, and Rosen paper, has led to a significant broadening and deepening of our understanding of quantum physics and its potential applications. Section 9. The continuing debate on quantum interpretations. Despite the experimental violations of Bell's inequalities, the debate concerning the interpretation of quantum mechanics and the meaning of quantum reality continues to this day. Various interpretations of quantum mechanics exist, each offering a different perspective on the nature of measurement, the role of the observer, and the underlying ontology of the quantum world. These interpretations include, but are not limited to, the Copenhagen interpretation, Bohmian mechanics, the Manuel's interpretation, and consistent histories. Each interpretation adheres to the same mathematical formalism of quantum mechanics, yet each provides a distinct conceptual framework for understanding its implications. The ongoing debate reflects the profound challenges that quantum mechanics poses to our classical intuitions about reality, causality, and locality. The search for a deeper understanding of quantum mechanics continues to drive both theoretical and experimental research, pushing the boundaries of our knowledge about the fundamental nature of the universe. The Einstein, Podolsky, and Rosen paper remains a central point of reference in these discussions, its enduring legacy stemming from its incisive questioning of the foundations of quantum mechanics. Section 10. Assessment of the APR arguments. Validity in light of subsequent discoveries. Considering the advancements in quantum mechanics and experimental verification since 1935, one must re-evaluate the validity of the Einstein, Podolsky, and Rosen paper's central argument. While the paper's initial premise, the definition of physical reality, remains a subject of philosophical debate, the experimental violation of Bell's inequalities has undermined the assumption of local realism upon which their argument heavily relies. The experiments have shown that the universe does not behave in the way that Einstein, Podolsky, and Rosen expected, and that quantum mechanics, despite its seemingly strange features, accurately describes the observed phenomena. While it is true that quantum mechanics may not provide a complete picture of reality in the sense that Einstein, Podolsky, and Rosen envisioned, it is a remarkably successful and accurate theory that has revolutionized our understanding of the physical world. The paper's enduring value lies not in its success in disproving quantum mechanics, but rather in its profound questioning of the foundations of physics and its stimulation of research into the fundamental nature of quantum reality. The Einstein, Podolsky, and Rosen paper serves as a reminder that scientific progress often comes from challenging established assumptions and pushing the boundaries of our knowledge. Conclusion. The 1935 paper authored by Albert Einstein, Boris Podolsky, and Nathan Rosen, Can Quantum Mechanical Description of Physical Reality Be Considered Complete? Stands as a seminal work in the history of physics, prompting extensive discussion and rigorous investigation into the foundations of quantum mechanics. While the paper's central argument, asserting the incompleteness of quantum mechanics based on a specific definition of physical reality and the assumption of locality, has been challenged by subsequent experimental results and theoretical developments, its impact remains undeniable. The violation of Bell's inequalities has cast doubt on the assumption of local realism, a cornerstone of the Einstein, Podolsky, and Rosen argument. Nevertheless, the paper's incisive questioning of the nature of quantum reality stimulated the development of hidden variable theories, deepened our understanding of quantum entanglement, and paved the way for the field of quantum information theory. The Einstein, Podolsky, and Rosen paper acts as a powerful reminder of the importance of critically examining the assumptions underlying our scientific theories and of the ongoing quest to comprehend the fundamental nature of the universe. Its legacy endures not as a refutation of quantum mechanics, but as a catalyst for profound insights into the complexities and counterintuitive aspects of the quantum world, and as a constant source of intellectual ferment within the physics community. The continued relevance of the Einstein, Podolsky, and Rosen paper lies in its enduring ability to provoke discussion and inspire new avenues of research, ensuring that the fundamental questions about the nature of quantum reality remain at the forefront of scientific inquiry. The work represents a pivotal moment, challenging established paradigms and forcing a deeper consideration of what constitutes reality at the quantum level.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.